almost 38 years. Before that, I was with a private engineering company. So I've been doing dam safety since 1979. And I recognize a few other old timers in the attendee list. So let me go ahead and get started. If you can see the background, the virtual background I have, it's a dam in Wisconsin that a couple years ago, it was a flood control dam that was built in the 1960s by NRCS and had been there for 40 or 50 years. And during a big thunderstorm a couple years ago, there was flow through the emergency spillway. And as you can see, if I move out of the way a little bit, the entire reservoir was lost through the emergency spillway when it breached to the full depth of the dam embankment. So that's what prompted us to send out to owners of NRCS flood control dams of the same vintage to look at their emergency spillways. Okay. So this presentation is intended for soil conservation districts and stormwater reviewers who look at small pond designs for compliance with NRCS MD 378 standards. Some of you have seen some of my presentation before, but there's some new material as well. Design and construction of a dam is a somewhat inexact science, and engineers are continually called upon to exercise their judgment in order to anticipate and provide for site factors which are not precisely known ahead of time. It is important to note that the MD 378 standard establishes the minimum acceptable quality for the design and construction of ponds, and that's straight out of MD 378. But it does not set the standard of care that is normally expected of the design engineer. There will be times when something more than the minimum will be required, and the designer will need to include additional provisions in order to ensure the safety of the structure. If, as a reviewer, you raise an issue that the designer is unwilling to address, or you are uncomfortable with the design, then the SCD always has the option to refuse to issue its approval and require that the applicant obtain a permit from the department. One thing that we often see is that the proposed cutoff trench under the dam embankment is shown as the minimum required in MD 378 without any consideration for the foundation soils. Note that 378 requires the cutoff to extend as deep as needed to reach impervious soils. That is why you need borings at the pond location. If the cutoff does not extend to the impervious stratum, then MD 378 requires seepage controls. Such controls would include trench drains at the toe, rock toe, blanket drains, chimney drains, etc. Sequence of construction is important. So a lot of times we get a question from a developer saying, what's wrong with the contractor building the embankment first and then cutting a notch through it to put in the spillway barrel? That's how we do road culverts, and the contractor says they can get the job done faster and better, get better compaction on the embankment. Well, 378 says that the spillway must be installed concurrently with fill placement and not excavated into the embankment. And there's a reason for that. Part of the reason is that in a trench excavation, the side slopes create the potential for arching of the backfill. So the fill will bridge over the spillway pipe, which reduces the soil pressure on and along that pipe. If the reduced soil pressures are less than the hydrostatic pressures from the impoundment, then the soil can wash away by seepage, as shown in this slide. Here is an example showing a void that formed alongside of a spillway that had been installed in a trench. And one of the layers of compacted fill washed away. I don't know if it was a different material or a different compaction spec or a different compaction effort, whatever. You can still see the impressions of the equipment on the upper lift of soil and the near vertical sidewall on the left side of the picture. So placing a pipe in a trench is a big no-no because it can cause failure. There's also potential when you put in fill in a trench, it'll be compacted differently than the rest of the embankment. So there's a potential for differential settlements that can create cracks and seepage potential between the pipe backfill and the embankment fill. Here's a pond which failed a month after construction completed. During the final inspection a month earlier, it looked pretty good. Here's the upstream side. And here's the downstream side. For scale, the outfall pipe is a 42-inch corrugated metal pipe, and the embankment is about 15 feet high. but you need to know something about how it was constructed. The pipe was not installed in accordance with MD 378. In this case, the embankment was constructed and a notch was cut through it for the spillway installation. And this is about 20 years ago. Actually, it's exactly 20 years ago. The first time that the 15-foot high dam had to impound water, the fill along the pipe washed away. You can almost see the sides of the trench that they had excavated, put that pipe in. All the backfill washed away. And the resulting sediment discharge impacted a trout stream in Cecil County. Here's another picture of from the downstream side. The pond was not repaired since it was no longer needed for and stormwater management was accomplished by putting a stone weir and a riprap channel through the breached area in the embankment. The stormwater pond in Anne Arundel County failed shortly after it was constructed. It had a concrete riser and a corrugated metal pipe, and you can see the remnants of an anti-seep collar behind the man standing in the center of that picture. I'm seeing in the chat that somebody says the 5-minute break slide is still there. Is that correct?
No, that's not correct.
Oh, okay, very good. Thank you. And here is a PVC pipe that was used for a spillway in a pond, a fairly small pond, obviously. It looks like about an 8-inch pipe. But they had put a plastic filtered anti-seep collar on it. Didn't work. There is a special case where a trench can be used, and that's for replacement of a failed spillway pipe that runs through a pond embankment or a dam embankment. But the side slopes of such a trench should be no steeper than 2H, 2 horizontal, to 1 vertical. And that is to minimize the potential for bridging of the new fill over the pipe to reduce those soil pressures that I mentioned before. In this case, the engineer shows 1 to 2, and that's not the usual ratio. Usually you'd put 2 to 1, 2 horizontal to 1 vertical. So I don't know if the engineer is expecting this slope to be flat, 2 to 1, horizontal to vertical, or very steep. And I didn't redraw this sketch. It's highly distorted. But the engineer should label it. So if it's 2 horizontal to 1 vertical, that's what it should say on that drawing. So there's no confusion and no misinterpretation on the part of the contractor. Also, the trench doesn't include the old pipe. It just says existing 24-inch CMP to be removed. Well, how? So really, the excavation should have been much larger in this case. And if you notice, the engineer's proposed excavation didn't leave any room alongside the concrete cradle. They're putting a new concrete pipe in. And a cradle is required in that case, but you have to have enough room on both sides of the cradle in order to compact the backfill against it. So the trench needs to be much bigger. And a lot of times when you take out this much material, you end up taking most of the dam embankment out anyway for smaller structures. And one last thing is, I'm going to talk about filter diaphragms. That if you're putting in a pipe in a trench, a filter diaphragm for seepage control should extend past the sides of the trench in order to intercept any potential seepage that could occur at that transition zone. So anti-seep collars don't prevent seepage failures, and MD 378 says that filter and drainage diaphragms are always recommended, not required, but they are required, as in item 2, for embankment soils with a high piping potential, such as unified classes GM, SM, and ML. Well, I think that covers most of the soils in Maryland, because a lot of the soils are in the coastal plain are erodible. In the Piedmont physiographic province, they're micaceous, silty soils, sandy silts. They're very erodible. So I think every dam and small pond should include a filter diaphragm for seepage control. The exception would be soils that are highly plastic, clays and silts, such as CH and MH. However, these aren't even generally suitable for use in pond embankments. Spillways on the dam embankment. Spillways not a good idea and will not be approved. Although I'm sure that the artist of this drawing didn't intend it, the picture shows a potential problem. There's no water going over the spillway at the top of the picture, right in the middle, but there is a blue area and a stream coming out from under the downstream side of the spillway, and that's pretty typical. They almost always fail. Eventually, they all fail. When faced with the issue of an older dam with a failed corrugated metal pipe spillway, many owners will ask us why they can't just fill the pipe with concrete and put a concrete structure over the dam embankment. And here's one reason why that's not going to be approved. This is a picture of a larger dam that was designed by a federal agency, a large federal agency, and they put underneath it what they thought would be adequate controls for seepage and prevent piping of embankment soils underneath the spillway, but didn't work. Here's a chute spillway on a dam in Maryland, in St. Mary's County, on a 30-foot high golf course dam in St. Mary's County that was installed 40 years ago. You can see the bottom third of that structure has broken up and fallen into a void. And if you looked under that structure, you'd see a 3-foot high void as far up as you could see under that structure. And here's another one in Woodlawn in Baltimore County. John will talk about this a little bit. He has the same picture, but this is a brick riser that was approved for a small pond. I'm not even sure where, but it looks pretty, but they don't meet MD 378 because they're not designed to accommodate the hydrostatic pressures exerted by impounded water, and then they collapse. I'll talk briefly about precast risers. So a number of years ago, we had approved precast risers for some dam spillway. And we required that the sections be anchored together so that the whole thing would act as a monolithic structure similar to a cast-in-place riser. This particular structure, it turned out, had insufficient reinforcing steel, longitudinal steel, to prevent these walls, long walls, from cracking as the walls deformed from the embankment backfill. It's also really difficult to create watertight joints that will remain watertight for the life of the structure. So the anchor plates that were installed on another structure, the manufacturer had put slots in them to, I guess, to help the contractor line the bolts up. But the way the slot was cut into the strap would not prevent movement of that joint. So the movement in this joint is vertically, but the slot in that strap is vertical, so that if there was any movement, the slot was just going to slide. I mean, the bolt was just going to slide in the slot, so it wouldn't have done any good at all. So we will approve or consider approving precast risers if they're less than 10 feet high and they can be manufactured in one piece, so there are no joints, and that the barrel connection can be made watertight. But we've seen cases where the engineer specified certain wall and footing thicknesses to ensure that there be sufficient mass for protection against flotation, but the precast manufacturer, because of weight considerations, would lighten the structure so they could ship it, make the walls thinner, and they said, well, we have the same strength wall because we increased the concrete strength to compensate for it. Well, then it doesn't have sufficient flotation, anti-flotation mass. This particular structure shows gravel under the fill, under the gravel fill placed under the structure, because contractors like to do that because it's easier to adjust the structure for line and grade. But foundation under the spillway should be undisturbed, impervious natural ground, and where the soils are unsuitable, it should be removed and backfilled with a lean concrete mud mat. And also in this picture, the man is standing on a homemade ladder or a site-made ladder in a trench or on a hole that has sidewalls that exceed the OSHA requirements. Just an aside. I mentioned before that it's important to have a boring at the location of the dam. Probably ought to have more than one, so that the design engineer knows how deep to take his cutoff trench and what kind of foundation soils to design his filter diaphragm. A lot of times though, the owner hires a geotech and provides the borings to the designer of the dam, but they aren't usually located in the pond area and none along the spillway. And sometimes the engineer doesn't even look at that report and they just plop down a standard design. MD 378 says a soils investigation is required for all ponds, and at a minimum, it should include information along the center line of the dam and in the emergency spillway. The engineer should also require borings. This is where you go above and beyond what 378 says. The engineer should also require borings at the proposed riser location. Make sure it's suitable. Excuse me for a second. I want to talk briefly about trash racks. MD 378 says that spillway structures that have flow over the top, like a riser, should have a non-clogging trash rack, such as a hood type inlet extending at least 8 inches below the weir opening, which allows the passage of water from underneath the trash rack into the riser. All pipe and inlet structures should have a trash rack. Openings for trash racks should be no larger than half of the barrel conduit. In this case, it's about 3-foot diameter pipe. And in no case should the openings be less than 6 inches. So there's an NRCS publication called TR60, which talks about dams and reservoirs, which has some criteria about sizing any trash racks. And it says that the average velocity of flow through a trash rack should not exceed 2.5 feet per second under the full range of discharge for the spillway. And low-level outlets, that's further a velocity of not more than 2 feet per second. And the velocity is based on the net opening area of the trash rack. So that is to keep the velocity low enough so that trash isn't drawn toward the spillway. And it also increases the surface area so there's more room for flow to get through in case there is debris that's pulled into the trash rack. In this case, there's not very much open area. The intent is that a trash rack will prevent clogging of the spillway pipe. This is a hooded riser, a standard NRCS hooded riser, which was in use for decades in Maryland. We used to see every pond had a structure like this in it. It has a hood which extends out from the riser by several inches and extends below the water surface. This allows clean water to enter the riser from underneath and keeps floating debris from getting into the spillway. This is a poorly designed trash rack because it doesn't extend below the water surface. And also the angle iron effectively raises the riser crest by a couple of inches. Here's a better design that we approved, but it has a big flat expanse, which is still prone to clogging, and it probably should be sloping instead of big and flat. This was a cone-shaped manufactured trash rack for a dam in Salisbury that looked great on paper, but it turns out that it does not work well in the watershed in which it is located, and it collects a lot of debris, and it's a never-ending maintenance issue. Here's a couple of trash racks on a riser in Western Maryland. They're better than the flat grate right across the, but the engineer should check to ensure that they meet the requirements in NRCS TR60 for flow area and flow velocity. So as I mentioned earlier, trash racks should be designed to hold back large debris that would obstruct the conduit, yet allow smaller debris to pass through. Otherwise, they'll become obstructed. Here's one in Montgomery County. The photo in the upper left shows the openings in the trash rack during normal conditions. The picture at the right from inside the riser shows small debris that's been trapped by the trash rack, effectively blocking the entire lower half of that opening in the center of the riser. Switching gears a little bit, we'll talk about factors of safety. So if you're designing a pond or submitting a pond for review and approval to the local soil conservation district, MD 378 says factor of safety shall be 1.2 for flotation of the riser. But if for some reason you have to submit that to MDE, we have a problem in that all factors of safety in COMAR have to be at least 1.5. So right off the bat, if your riser only has a factor of safety 1.5, we're going to require you to demonstrate that it has a if you design it for 1.2 and submit it to us, it has to meet 1.5. You have to demonstrate that or redesign it. And I have a question. What should we do about this inconsistency? Some other review issues are emergency or principal spillways which discharge along the toe of the dam embankment, or an embankment that's constructed along the edge of a pond, a stream, often in the 100-year floodplain. Something else that we see is the inclusion of geotextiles or filter fabrics in drains in the dam embankment. We're not going to approve that. Filter fabric is not allowed for construction of filters and filtered diaphragms because they can clog. It's hard to put them in without getting any wrinkles. A wrinkle can allow migration of seepage flow and soil particles along the plane of the fabric. So they have to be put in without wrinkles. And it's really hard to get them around pipes and other projections without introducing wrinkles or tears. They're not allowed from drains. Basically, they're not allowed inside a dam embankment where they'd be really hard to dig up and replace when they clog. That's the other problem, is they tend to clog. If not with soil particles, with iron ochre bacteria. Filters should be properly designed according to NRCS NE8, National Engineering Handbook, Chapter 26. So if you have a multi-stage filter of sand and gravel around a pipe, the sand should be properly designed, gradation, so that it does not wash into the gravel. And the gravel should, the holes in the pipe should be designed so that the gravel doesn't pass through. And that's all covered in this publication. Geotextiles are acceptable for use under riprap, and it can be replaced in the future if needed.
8 minutes left.
Thank you. I want to talk a little bit about utilities and dam embankments, especially if the pond embankment or the dam embankment serves as a county road or a community road. The counties say, well, we do it all the time. What's the big deal? It's our road. We need to install the water, sewer, gas mains there. And as we learned yesterday, a lot of times there's fiber optic telecommunications cables buried in these embankments. And if the dam were to fail, those utilities, critical utilities, would also likely be broken. So that may result in us changing the hazard classification of the dam, because Comar says if failure of the dam causes a disruption of public utilities, then it's not low hazard. The other thing is the utilities in the pond embankment need to be shown on the drawings that the SCD will review for small pond approval. MD 378 says pipes and utilities that are not parallel to the axis of the dam, that means they go upstream to downstream, they need to meet all the principal spillway requirements: filter diaphragm, concrete cradle, and proper compaction of embankment soils. Pipes that run parallel to the axis of the dam, like along the center line of the road, have to be constructed with no granular bedding. They should also be watertight. And any future work, such as excavation to repair these utilities in the future, would require agency approval by the agency that originally approved the pond. So the approving agency needs to know about any utilities that are located in the dam. This is a stormwater pond in Maryland. It was approved by the Soil Conservation District as a low hazard, small structure. Not sure about the hazard classification because, as you can see here, we're looking along the downstream slope of this embankment. The top of the dam is the chain link fence at the left side of the picture, and the toe is the silt fence in the middle of the picture. And then there's the house. And the spillway is tied into an old railroad culvert, which runs under the road and under a nearby hiking trail. And shortly after construction of the embankment was finished, water and sewer pipelines were placed in vertical trenches excavated in the embankment, parallel to the dam axis along the toe of the dam. You can see the disturbed area in this image that I took from Google Maps. And when I questioned the SCD about why they approved the utilities in the embankment, it said they had no idea those utilities were going to be there because the county directs engineers to submit plans for stormwater without all the utilities because they thought the utilities would confuse the Soil Conservation District and make it too hard to evaluate. That is crazy. And I'm not saying the name of the county or the Soil Conservation District to protect the innocent. People who know about this project are mostly retired now. So not only was the sewer buried in the embankment, but a few months later, a pump station was installed right in the top of the dam embankment. A big hole was dug in, a prefab pump station was installed and backfilled. It probably was not backfilled properly. It compacted to the same standard as MD 378 requires, or the original design required. So utilities should always be located outside of the pond embankment. In the event they cannot be relocated, they need to be reviewed and approved as part of the pond design. In this case, this SCD had no knowledge of them. So under Maryland law, the installation of these utilities in the embankment would constitute a change, and therefore either a permit from approval from Soil Conservation District or a permit from SCD to put these into a previously completed embankment.
4 minutes.
Does that include the questions?
Yes, it does.
Uh-oh. Okay. I got a few more slides. So
Hey,
outfall
Hal,
design? Yes, sir.
we don't have any questions yet, so don't feel rushed.
Okay, very good. Outfall design, the pipe outfall should be designed for full pipe flow, not just the 10-year flow or whatever. Figure out what the full pipe flow is. And then there probably should be a plunge pool. A riprap ditch or level apron is not acceptable. And the NRCS Maryland office has developed a design guide, October of 2003. It's called NRCS Design Guide MD number 6. And here's an example. It applies to pipes up to 30 inches in diameter. Tells you how big a plunge pool you need and how big the riprap and how thick a layer of riprap it ought to be. Some other things to consider, because I don't have time to cover everything today, is what changes do we need to make to COMAR regulations? I know everybody has ideas on that. John's going to talk about it a little bit, but we're open to your suggestions. What changes do we need to make, should be made to NRCS MD 378? It's an NRCS publication, but as John will mention, we'd like to be involved in rewriting MD 378. One of our pet peeves is cross sections on the plan should be shown as perpendicular to the center line of the embankment rather than along the principal spillway pipe, which is often at an angle through the embankment. Engineers will measure the height of the dam at the spillway pipe location without recognizing that the lowest point on the embankment might be at another location, especially if there's a road with a vertical curve. So the pipe might not be at the low point. The core and cutoff trench should run the entire length of the embankment up to the design storm elevation. We suggest the use of ACI 350 as the design standard for concrete rather than ACI 318. ACI 350 calls for thicker walls and closer rebar spacing, sometimes 2 layers of rebars, to minimize cracking. And cracking is not really something you want to see in your pond spillway, so it's better to use the environmental concrete standard ACI 350 to minimize cracking. And we see issues with construction inspection all the time. Who does the construction inspection in your jurisdiction? It should be under the control of the engineer rather than the contractor, or it should be under the direction of the owner. And there are so many construction issues that we see. That's a topic for another workshop altogether. So send a list of things to consider and by chat or send an email to Stu Comstock. So we do have a minute or two for questions if there are any.